We're going to dive into some truly mind-bending topics tonight. We'll explore things that make even the most seasoned space experts scratch their heads. It's not about being afraid, it's about being utterly bewildered. Because out there, beyond our world, we've found things that just don't fit. These are phenomena that, according to everything we understand about the cosmos, shouldn't really be there. They seem to break all the accepted guidelines. And I'm not talking about fantastical stories or unproven ideas. We're discussing actual observations, real measurements we've taken. These are objects and events existing right now, doing whatever peculiar things they do, and we truly have no idea why. For many years, our tools for looking into the distant expanse were relatively simple. We saw what we could, and we built our understanding of the universe around those observations. But as our technology has advanced, as our instruments have become incredibly sensitive, a new picture is starting to emerge. Over the last few decades, as our viewing devices have grown more powerful, and our capability to study the cosmos has sharpened, we've encountered findings that have really challenged scientific thought. Some of these discoveries push the boundaries of what we thought was possible in physics. Others hint at universal processes that are still completely unknown to us. And some are just deeply, profoundly strange. They stand as silent, baffling questions in the vastness of space, waiting for us to uncover their secrets. Let's begin our journey into the unknown with an event that happened on August 15th, back in 1977. A man named Jerry Eman was going through information from the Big Air Radio Telescope, located at Ohio State University. This telescope was a crucial part of SETI, which stands for the Search for Extraterrestrial Intelligence. Day after day, this instrument patiently scanned the sky, listening for any kind of radio signal that might suggest intelligent beings were out there, somewhere. Most of the time, the data was pretty dull. It was just the usual background hum of the universe. Nothing special ever turned up. But on that particular day, Eman saw something truly extraordinary. It made him grab a red pen and scrawl WOW in the margin of the printed output. That's precisely why we still call it the WOW signal. This peculiar signal lasted for a remarkable 72 seconds. During that brief window of time, its strength was an astonishing 30 times greater than the normal background noise from space. It emanated from a very specific region in the constellation known as Sagittarius. And here's the part that makes it so incredibly intriguing. The signal's frequency was right around 1420 MHz. This frequency is extremely significant because it's precisely where the hydrogen line is found, a natural frequency naturally linked to hydrogen atoms. Why does that particular detail matter so much? Well, hydrogen is the most abundant element throughout the entire universe. It literally makes up the vast majority of all ordinary matter. If you were an intelligent civilization, attempting to send a beacon out into the cosmos that other intelligent beings might easily recognize, choosing a frequency tied to hydrogen would be a logical, almost universal, language choice. It would be like trying to communicate using a fundamental constant that everyone, everywhere, would intuitively understand. The Big Air Telescope was designed with 2 receivers. These receivers would scan the identical patch of sky, but with a precise 3-minute delay between them. The perplexing thing was that this powerful signal appeared on the first receiver, but it was completely absent from the second. This strongly suggests that the signal's duration was less than 3 minutes, probably much closer to the 72 seconds indicated by the initial data. Since that remarkable moment in 1977, astronomers have repeatedly turned their gaze back to that same exact spot in the sky, time and time again. They've deployed far more powerful telescopes. They've listened intently at the original frequency and at nearby frequencies, hoping for even a faint whisper of its return. They've searched tirelessly for any indication that this unique signal might come back. But, to this day, there has been nothing. The WO2 signal remains a solitary one-time occurrence. Now, let's be absolutely clear about the inherent uncertainty surrounding this event. This signal could have been artificial, meaning it was sent by some intelligent source, or it could have been entirely natural. The Big Air Telescope, while capable of detecting powerful signals, wasn't designed to pinpoint locations with extreme precision. So, while we know the general direction from which it came, we can't identify its exact source with certainty. Some scientists have proposed various natural explanations to account for it. Perhaps it was a burst of radio waves from a passing comet. Comets, as they journey through the solar system, can indeed emit radio waves when the solar wind, a stream of charged particles from the sun, interacts with the vast clouds of hydrogen that surround them. In 2016, a researcher named Antonio Paris put forward the idea that specific comets, known as 266 Piers Christensen and P28Y2, were actually present in that particular region of space at the exact time the signal was detected. However, there's a significant problem with this comet theory. The signal itself was incredibly narrow band. It occupied a very precise and confined frequency range. Natural sources of radio waves, like comets or pulsars, typically produce signals that span a much broader spectrum of frequencies. The extreme narrowness of the WO2 signal is actually far more consistent with an artificial origin, something deliberately transmitting on a carefully chosen frequency. Other scientists have suggested it might have been interference originating from Earth itself. Perhaps a passing satellite, or an aircraft, or even some ground-based transmitter, just happened to send a signal at precisely the right moment. But the Big Air Telescope was specifically engineered to filter out terrestrial interference. Furthermore, the signal came from a direction that wasn't consistent with the known trajectories of any satellites or aircraft operating at that time. So, what exactly was it? Honestly, it remains completely unexplained, and that's precisely what makes it so endlessly fascinating. Nearly 50 years later, the WO2 signal stands as one of the most intriguing and baffling, unexplained observations in the entire history of CTI. The fact that it never repeated is both deeply frustrating for researchers and incredibly significant in its implications. If it truly was a message from an advanced alien civilization, why would they only transmit it once? Perhaps they were employing a kind of lighthouse strategy, sweeping a powerful beam across the galaxy, and we just happened to be in the right place at the right time to briefly catch a glimpse of it. Maybe it was a one-time broadcast, a singular event that wasn't meant to be repeated. Or perhaps it wasn't intended for us at all. It could have been an accidental spillover from some other form of communication between two distant points. Then again, maybe it wasn't aliens whatsoever. It could have been some entirely natural phenomenon that we simply don't understand yet. The universe is absolutely brimming with various processes that generate radio waves, pulsars, quasars, magnetars, the remnants of supernova explosions. We are constantly discovering new and unexpected types of radio sources. Perhaps the WO2 signal was simply a manifestation of something natural that we've just never encountered before or since. The truth is, a definitive answer may never materialize. The signal lasted a mere 72 seconds in 1977 and has never returned. It exists as a mystery, effectively frozen in time, but it also serves as a potent reminder of just how much about the universe remains utterly unexplained. Somewhere out there, in the general direction of Sagittarius, something emitted a powerful, narrow, band radio signal, and we happened to catch it. That's either the most incredible coincidence in the entire history of astronomy, or it represents compelling evidence of something truly extraordinary. Either way, it's profoundly strange, and it's precisely why, almost 5 decades later, people are still discussing the WOW signal with such intense curiosity. Now, let's shift our focus to something that's actively happening right now, a star that has been perplexing astronomers since 2011. Its formal designation is KIC 846285, but most people affectionately refer to it as Tabby's star. This name honors astronomer Tabitha Boyajian, who was the lead researcher on the team that initially studied this enigmatic object. Tabby's star is located approximately 1,460 light years away from us, nestled within the constellation Cygnus. From a casual glance, it appears to be a perfectly ordinary star. It's slightly larger and a bit hotter than our own Sun, but there's nothing visually or fundamentally about it that should make it unique. However, in 2011, the Kepler Space Telescope, which was designed to search for exoplanets, noticed something truly bizarre. Stars do dim sometimes. That's completely normal. If a planet passes directly in front of a star from our vantage point, the star's light will momentarily drop by a very slight amount. This is precisely how we detect many exoplanets. For example, if Earth were to pass in front of the Sun from the perspective of another star, the Sun's light would dim by a tiny fraction, around 0.01%. This is small, but it's measurable. Jupiter, being much larger, would cause the Sun to dim by about 1% if it transited. This is the kind of dimming we expect from planets. It's regular, it's predictable, and it's always a small reduction in brightness. Tabby's star doesn't follow these rules at all. In 2011, its light unexpectedly dropped by an enormous 15%. Then, it returned to its normal brightness. In 2013, it dimmed again, this time by an even more staggering 22%. And then, once more, it brightened back up. The pattern of these dimmings was completely irregular. They didn't occur at predictable intervals, and they didn't last for consistent amounts of time. Sometimes the star would dim a little, sometimes a lot. A 22% dimming is truly enormous. That simply cannot be caused by a planet. A planet the size of Jupiter would only block about 1% of the star's light. To block a full 22%, you would require something absolutely massive, something potentially as large as the star itself. This initial discovery immediately sparked a flurry of theories and intense speculation within the scientific community. What could possibly be obscuring so much of the star's light? This is where things became truly captivating. Someone, in a moment of daring hypothesis, suggested it might be an alien megastructure. This audacious idea stems from a hypothetical concept called a Dyson sphere, which was proposed by the brilliant physicist Freeman Dyson back in 1960. Dyson pondered what an extremely advanced civilization might do if its energy needs became truly astronomical. He reasoned that, eventually, they might construct immense structures around their home star to effectively capture and utilize its entire energy output. Not a solid shell, which would be an impossible feat of engineering, but rather a vast swarm of energy, collecting satellites or habitats, all orbiting the star. If an advanced civilization were indeed building something like that, it would naturally block varying amounts of the star's light as the complex structure moved around it. This blockage would be irregular, not planetary. It would cause the star to dim by substantial amounts. In essence, it would look exactly like the perplexing phenomenon we were observing with Tabby's star. Now, before anyone gets too carried away with this exhilarating thought, let me be very clear. The vast majority of astronomers do not believe that Tabby's star is an alien megastructure. The alien hypothesis was always considered the least probable explanation. But here's the crucial point: scientists felt compelled to consider it, because they couldn't explain the observations in any other conventional way. That's how genuinely peculiar this particular star is. So, if it's not intelligent alien life at work, what is it? Scientists have put forward several natural explanations. One idea was that there might be a colossal swarm of comets orbiting the star. If a massive family of comets were to pass in front of the star, they would indeed block its light in an irregular fashion. Their long, dusty tails would create uneven and unpredictable dimming effects. This was a leading theory for quite some time. However, there are difficulties with the comet swarm hypothesis. Where would such an enormous number of comets originate? You would need an absolutely staggering quantity of them, far beyond what we typically observe, to block a full 22% of the star's light. Moreover, comets, especially those with such extensive dust tails, would produce a lot of dust. This dust, when illuminated by the star, would cause the star to appear noticeably redder when it dimmed, as dust particles tend to scatter blue light more effectively. But Tabby's star doesn't do that. Its color remains remarkably consistent, even during its deep dimming events. Another theory suggested that perhaps a recent, massive collision had occurred near the star. If two very large objects were to violently smash into each other close to Tabby's star, the resulting debris cloud would certainly block light irregularly as it expanded and dispersed. But again, if this were the case, we would expect to detect an excess of infrared radiation, a telltale sign of warm dust. We simply don't observe that. Some scientists considered the possibility that the dimming might be intrinsic to the star itself. Perhaps it's a type of variable star that naturally dims in unusual ways. However, Tabby's star doesn't exhibit the characteristic behaviors of any known variable star types, and its dimming pattern is far too erratic and irregular to fit into existing categories. Then, in 2017, astronomers made another crucial observation. They managed to catch Tabby's star dimming once more, and this time, they observed it across a wide range of light wavelengths. What they discovered was incredibly interesting. The dimming effect was significantly more pronounced in blue light than it was in red light. This finding is highly consistent with the idea of dust particles obscuring the starlight. Tiny dust particles are known to scatter blue light much more effectively than they scatter red light. It's the very same physical principle that explains why Earth's sky appears blue to us. So, perhaps it truly is dust after all. But if it is dust, where is such an immense quantity of it coming from? Why is there so much of it? And why is its pattern of obscuration so incredibly irregular? The most recent observations suggest that Tabby's star might be surrounded by a vast and complex debris field. This field could potentially be the remnants of a destroyed planet, or the aftermath of some other colossal, catastrophic event in the star's history. This swirling debris would then irregularly block the star's light as it orbits. This is currently the leading explanation, but it still doesn't fully answer all the questions. The complete picture of what's happening remains shrouded in mystery. And here's what makes this entire situation even stranger. Tabby's star is still doing it. We've now observed this star for over a decade. It continues to dim in these bizarre, unpredictable ways. We possess multiple sets of data from various telescopes, all confirming the phenomenon. It's not a measurement error. It's not a temporary glitch in the equipment. Something is genuinely blocking the light from this star in ways that continue to deeply puzzle us. As of 2025, Tabby's star remains one of the most enigmatic objects in the night sky. Out of the hundreds of billions of stars we've cataloged, this is literally the only one that behaves in this manner. We have never encountered anything else quite like it. Perhaps one day we will finally unravel its secrets. Maybe we'll discover it's a natural process we simply haven't observed before in such an extreme form. Or perhaps, just perhaps, it's something else entirely. Something so fundamentally different that we haven't even conceived of it yet. Let me now introduce you to something scientists stumbled upon in 2019 that, quite frankly, absolutely shouldn't exist. They're called odd radio circles, or ORCs for short. The name is perfectly fitting because they are genuinely odd. They are perfectly circular, and we can only perceive them using radio wavelengths. Here's what they actually look like. If you aim a radio telescope at certain specific parts of the sky, what you observe is a perfect, almost flawlessly rendered circle. This circle is absolutely enormous, stretching for hundreds of thousands of light years across the cosmic canvas. And here's the truly bizarre part. There's almost always a galaxy located right at its very center. The very first of these strange structures was discovered by a research team led by astronomer Ray Norris. They were utilizing the Australian Square Kilometre Array Pathfinder telescope, known as ASCAP, to survey the radio sky. ASCAP is exceptionally sensitive to radio waves, which means it perceives the universe in a fundamentally different way than traditional optical telescopes do. When Norris's team processed the vast amounts of data they had collected, they were stunned to find these distinct circular structures. Initially, their immediate thought was that it must be some kind of error in their data processing. Circles are inherently suspicious in the field of astronomy. Nature, more often than not, rarely crafts objects with such perfect, geometric precision. But upon meticulously checking and re-checking their data, the team confirmed that these circles were indeed real. They then proceeded to find 3 more of them. Soon after, other telescopes independently confirmed their existence. As of 2025, we've identified about a dozen of these ORCs. They are remarkably rare, they are staggeringly large, and their fundamental origin remains a profound mystery. Let me try to describe exactly what we're observing. Each ORC manifests as a ring or a shell of radio emission. The ring's shape is almost perfectly circular, sometimes appearing to be flawlessly so. At its very heart, there's typically an elliptical galaxy. This central galaxy appears completely normal when viewed through optical telescopes. There's nothing overtly apparent about it that would immediately explain the colossal radio ring encompassing it. These rings are truly enormous. Some of them span more than 1 million light-years across. To put that into perspective, that's roughly 10 times the total diameter of our own Milky Way galaxy. These are structures on an absolutely monumental scale. Now, astronomers do occasionally observe circular formations in the sky. Sometimes, for instance, the remnants of a supernova explosion can appear circular. These are the expanding shells of debris left behind after a massive star violently explodes. However, supernova remnants are significantly smaller in scale, and they are always associated with relatively recent stellar explosions. ORCs are far too large and far too distant to be categorized as supernova remnants. Planetary nebulae can also exhibit circular appearances. These are the beautiful shells of gas shed by dying stars in their final stages. But once again, they are much smaller and are found exclusively within our own galaxy. ORCs are definitively not planetary nebulae. Some galaxies are known to have radio lobes, where powerful jets of matter, ejected from a central supermassive black hole, blast out into space. These jets can sometimes create circular structures when observed from specific angles. However, ORCs do not match the known characteristics of these active radio galaxies. The galaxies found at the centers of ORCs generally do not display the active, feeding supermassive black holes that would be necessary to generate such immense structures. So, what exactly are they? Honestly, we still don't know. Scientists have put forward several speculative theories. One idea is that they could be colossal shock waves resulting from enormous explosions occurring in the very centers of galaxies. If a galaxy were to undergo an intense period of star formation, a burst of energetic events, or if its central black hole were to suddenly become highly active, it could generate a powerful blast wave that expands rapidly outward. Over millions of years, this expanding wave might create a spherical shell of radio emission. But if this is the case, then why don't we observe more of them? Galaxies frequently go through active phases. We should, theoretically, be seeing these structures much more often. Another theory suggests they might be connected to merging galaxies, when all sorts of wild events can unfold. It's plausible that such a violent interaction could generate powerful shock waves that ripple outwards, forming these massive spherical shells. Yet, this theory faces the same difficulty as the previous one. Galaxy mergers are actually quite common throughout the universe. If collisions were the cause, we should be seeing far more ORCs than the handful we've currently found. Their scarcity is a real puzzle. Some scientists have ventured into even more unconventional territory, proposing highly exotic explanations. Perhaps these circles are residual imprints from truly primordial events that occurred in the very early universe, moments after the Big Bang itself. It's also been suggested they could be connected to hypothetical cosmic strings. These are theoretical one-dimensional defects in the fabric of spacetime, predicted by some advanced physics theories, but never directly observed. If cosmic strings truly exist, they could potentially act as cosmic scaffolding, influencing how large-scale structures like galaxies form and distribute themselves, possibly creating patterns like these. However, these ideas are still purely speculative. We have no direct proof that cosmic strings are real. The truth is, we're very much in the initial stages of understanding ORCs. We've only known about them for a few short years. To truly unravel their nature, we need a lot more information. We need to find more of them, scattered across different parts of the sky, to see if there are common characteristics or variations. We also need to study the central galaxies within these circles in far greater detail. What's special about these galaxies, if anything, that might trigger such an enormous radio emission? What makes ORCs particularly compelling is that they represent something entirely fresh and unexpected. Astronomers have been meticulously surveying the radio sky for many decades, gathering vast amounts of data. But ORCs only began to appear in our observations when we developed and deployed much more sensitive radio telescopes. This suggests they were always there, silently existing in the vast cosmic expanse. We simply lacked the sophisticated instruments capable of detecting them until recently. This tells us something incredibly profound about the field of astronomy itself. The universe is undoubtedly filled with countless phenomena that we haven't yet discovered. Not because these things are actively hiding from us, but because we haven't yet built the precise tools or developed the right observational techniques to perceive them. Every single time we manage to construct a better telescope, or when we begin to observe the cosmos in a new range of electromagnetic wavelengths, we invariably uncover something completely unforeseen. ORCs are a perfect illustration of this principle. Nobody predicted their existence. No one was actively searching for gigantic radio circles surrounding galaxies. Their appearance was a total surprise, a completely unanticipated gift from the universe. And now, the challenge for astronomers is to decipher what these circles are and what deeper insights they can offer us about the fundamental workings of the universe. As of 2025, odd radio circles remain one of astronomy's great unsolved mysteries. We know they are real. We have a general idea of their appearance and immense scale, but the underlying cause, the mechanism that creates them, is still completely unknown. They stand as strange, silent structures in the radio sky, waiting patiently for someone to unlock their secrets. Now let's talk about something that truly challenges our understanding of the universe on a monumental scale. In 2021, again in 2024, astronomers announced the discovery of two absolutely enormous structures that seem to defy one of the most fundamental principles of modern cosmology. The first of these colossal formations is known as the Giant Arc. It was brought to light by Alexia Lopez, who was then a PhD student at the University of Central Lancashire. The giant arc is a vast arrangement of galaxies, stretching across an incredible 3.3 billion light-years of space. To be clear, this isn't the distance to the structure, this is its actual size. Imagine light, traveling at its astonishing speed, taking 3.3 billion years, just to journey from one end of this single structure to the other. To put that scale into perspective, the entire observable universe is estimated to be about 93 billion light-years across. This means the giant arc alone accounts for a significant fraction of that immense cosmic canvas. The giant arc is located approximately 9.2 billion light-years away from Earth. It appears to us as a gently curved arrangement of galaxy clusters, resembling a colossal archway across the distant heavens, hence its very fitting name. Then, in 2024, the very same research team made another astonishing find. They dubbed this new discovery the Big Ring. This is another truly enormous structure, measuring about 1.3 billion light-years in diameter. And, just like the giant arc, it's also situated about 9.2 billion light-years away from us. Here's the really striking detail. It occupies the same general region of the sky as the giant arc. Having two such immense structures, both in the same cosmic neighborhood and at roughly the same distance from us, is highly suspicious. It strongly hints that they might be connected or somehow related to each other. Now, you might be wondering why these discoveries pose such a significant problem for our current understanding. Allow me to explain. In the field of cosmology, which is the study of the universe's origin, evolution, and large-scale structure, there's a cornerstone concept called the cosmological principle. This principle essentially states that when you observe the universe on sufficiently large scales, it should appear roughly uniform. No matter which direction you cast your gaze, you should generally see the same average density of matter. The universe should be considered homogeneous and isotropic, meaning uniform and appearing the same in all directions when viewed on these grand scales. This principle is absolutely fundamental to our current understanding of the entire universe. It's deeply woven into the fabric of the standard model of cosmology, which is our prevailing framework for describing the cosmos. Furthermore, it's strongly supported by observations of the cosmic microwave background, that ancient light from the early universe, which shows us that the cosmos was remarkably uniform in its infancy. However, the existence of the giant arc and the Big Ring directly challenges this foundational principle. These structures are simply too large. According to the detailed calculations based on the standard model, cosmic structures shouldn't be able to grow larger than approximately 1.2 billion light-years. This is the theoretical upper limit, determined by how much time gravity has had to pull matter together and form these aggregations since the universe began with the Big Bang. The giant arc, at nearly 3.3 billion light-years across, is almost 3 times larger than this theoretical maximum. Even the Big Ring, at 1.3 billion light-years, is pushing right up against that boundary. If these structures are indeed real, and the evidence strongly suggests they are, then we're faced with a serious dilemma. Either our theoretical limit for structure size is incorrect, or something profoundly strange and unexpected is happening in the universe. It could mean that the cosmological principle doesn't hold as perfectly as we once thought. Perhaps the universe is much lumpier and less uniform than we believed on these vast scales. Or it might indicate that there are fundamental processes at play, processes we don't yet understand, that are capable of creating structures far larger than our current theories predict. Some astronomers have naturally questioned whether these structures are truly real, or if they might simply be statistical flukes. When you're looking at the distribution of countless galaxies across such immense distances, it's sometimes possible to perceive patterns that aren't genuinely there. our brains are hardwired to seek connections and order, and we might, by chance, spot a line or an arc of galaxies that is merely a random coincidence. However, Alexia Lopez and her team conducted meticulous statistical analyses. The probability of the giant arc being a completely random arrangement of galaxies is estimated to be incredibly low, about 1 in 6,000. That's a very small chance. The statistical significance strongly indicates that the structure is real. The numbers for the Big Ring are even more compelling, adding further weight to its existence, and the fact that both of these colossal structures are found in the same cosmic region makes the idea of a mere coincidence seem far less likely. So, if they are real, what exactly are they? One potential explanation relates to something called baryon acoustic oscillations, or BAOs. In the very early universe, sound waves, or pressure waves, traveled through the incredibly hot, dense plasma. These waves left a subtle, but measurable imprint on how matter is distributed throughout the cosmos. They essentially created a preferred scale, a characteristic size for the clustering of matter, which later formed structures. But the giant arc and the Big Ring do not match the expected size from these baryon acoustic oscillations. They are significantly, profoundly larger. Another hypothesis is that they might be connected to those aforementioned cosmic strings. If these hypothetical one-dimensional defects in spacetime actually exist, they could have acted as gravitational seeds or guides, causing galaxies to form preferentially along their paths, thereby creating these immense, string-like or ring-like structures. But, as mentioned before, cosmic strings are still highly speculative. We currently lack any direct evidence of their existence. The most unsettling possibility, for many cosmologists, is that our standard cosmological model is simply incomplete. It might mean that the cosmological principle, while generally useful, isn't as robust or universally applicable as we once assumed. Perhaps the universe does possess large-scale structures that we haven't accounted for in our current models. It could imply that, at the very largest scales, the cosmos is far more intricate and complex than our current theoretical predictions allow. This wouldn't necessarily mean that the Big Bang Theory is wrong. Instead, it would mean we need to refine and expand our understanding of how cosmic structure formed and evolved within the universe. That's precisely how science advances. You make observations, you build models, and when those observations don't align with the models, you must update the models to better reflect reality. As of 2025, the giant arc and the Big Ring remain points of significant debate and controversy within the astronomical community. Some astronomers are thoroughly convinced that these are genuine, physical structures that undeniably challenge the cosmological principle. Others are more skeptical, suggesting they might be unusual statistical anomalies or perhaps misinterpretations of the vast amounts of data. What is abundantly clear, however, is that the universe, especially when viewed on its largest scales, is proving to be more complex than we initially thought. And these enormous structures, whether they ultimately turn out to be true anomalies or something else entirely, are pushing us to think much harder and more creatively about how the cosmos is truly organized. Let me introduce you to a place in the universe that is almost entirely empty. It's known as the Botes Void, and it stands as one of the most peculiar and mind-boggling features of the cosmic landscape. The Botes Void is a truly immense region of space, spanning approximately 330 million light-years across. To help grasp that scale, consider that it's more than 3,000 times the diameter of our entire Milky Way galaxy. It represents an enormous, staggering volume of space. Here's what makes it so profoundly strange. Based on the average density of galaxies observed throughout the universe, this particular volume of space should, theoretically, contain around 2,000 galaxies. That's what our models and observations of other regions would lead us to expect. However, when astronomers meticulously survey the Boötes void, they find only about 60 galaxies scattered throughout its vastness. The rest is, quite literally, an enormous expanse of emptiness. It's not completely devoid of matter. There are those few dozen galaxies, but compared to the expected abundance, it is remarkably, almost unnervingly, empty. That's precisely why it earned the name void. The Boötes void was initially discovered in 1981 by astronomer Robert Kirshner and his team of colleagues. They were engaged in a large-scale project to map the distribution of galaxies across the universe. And it was during this work that they stumbled upon this colossal, empty region within the constellation Boötes. At first, they were uncertain whether it was a genuine cosmic feature or simply an artifact of their survey methods. Perhaps they had overlooked some galaxies, or maybe their detection techniques weren't functioning optimally in that particular area of the sky. But subsequent observations, conducted with increasing precision, firmly confirmed its reality. The void is indeed real. There truly is a massive bubble of space out there with an almost complete absence of galaxies within it. Now, it's important to understand that voids themselves are not uncommon in the universe. The large-scale structure of the cosmos is often described as a cosmic web, a vast network of filaments of galaxies and galaxy clusters that intertwine and surround these immense, relatively empty regions. Most typical voids are tens of millions of light years across. They are a common and expected feature of this cosmic web. But the Boötes void is distinct. It is considerably larger than the typical voids we observe. In fact, it's one of the largest known supervoids in the nearby universe, and its sheer existence raises fundamental questions about how structure formed in the cosmos during its earliest epochs. Here's the thing about how the universe started. It began in an almost perfectly uniform state. The cosmic microwave background, which is essentially a faint echo of the Big Bang, shows us that when the universe was just 380,000 years old, matter was spread almost entirely evenly throughout space. There were minuscule density variations, tiny ripples in the otherwise smooth cosmic ocean, but they were incredibly small, on the order of 1 part in 100,000. Over vast stretches of cosmic time, gravity began to amplify these minute variations. Regions that were infinitesimally denser began to attract slightly more matter, growing even denser over time. Conversely, regions that were slightly less dense began to lose matter to their surroundings, gradually becoming emptier and expanding into voids. Computer simulations that model this process can successfully reproduce the cosmic web we observe today. The intricate filaments, the massive clusters, and the vast voids all emerge naturally from the inexorable pull of gravity acting on those initial, tiny density fluctuations. However, these simulations also predict certain limits. Voids, even with the relentless pull of gravity and the expansion of space, can only grow to a certain size, given the age of the universe and the fundamental strength of gravity. The Boötes void pushes right up against this theoretical limit. It is, in essence, about as large as voids can possibly get, according to our current theoretical understanding. This makes it particularly interesting because it serves as an extreme example. It acts as a natural laboratory, rigorously testing our understanding of how large-scale structures form in the universe. If our current models are accurate, we shouldn't encounter voids that are significantly larger than the Boötes void. If we ever did, it would strongly suggest that there's something fundamental missing or incorrect in our models of cosmic evolution. For now, the Boötes void just about fits within these theoretical limits, but it's right on the edge, and that makes it an object of intense and careful study. There's another intriguing aspect to the Boötes void. The few galaxies that do reside within its vast emptiness are, themselves, quite peculiar. Some of these isolated galaxies are forming new stars at unusually high rates compared to their counterparts in denser regions. Others exhibit unusual shapes or characteristics. It's as if their profound isolation has somehow influenced their development and evolution. Consider this: if you're a galaxy situated in a dense region of space, you're constantly interacting with numerous other galaxies. You're gravitationally tugging on them, and they're tugging on you. Sometimes, these interactions lead to spectacular collisions and mergers, reshaping galaxies and triggering bursts of star formation. You're also continually exchanging gas with your cosmic neighbors. In essence, you're part of a bustling, dynamic galactic neighborhood. But if you happen to be a galaxy in the profound solitude of the Bootes void, you are virtually alone. Your nearest galactic neighbor might be millions of light years away. You are evolving in almost complete isolation, shielded from the constant gravitational harassment and tidal forces that galaxies in denser regions routinely experience. This extreme isolation could dramatically alter how a galaxy evolves. Perhaps it retains a much larger supply of gas for longer periods, because there are no nearby galaxies to strip it away through gravitational interactions. Maybe its star formation processes unfold differently, without the external triggers or dampeners that interactions with other galaxies might provide. This unique environment could lead to the development of unusual characteristics over cosmic timescales. The galaxies within the Bootes void offer us a rare and valuable opportunity to study what happens to these colossal stellar islands when they are allowed to evolve in relative solitude. It's a vast, natural experiment that the universe itself has set up for us. But the fundamental question persists: why is the Bootes void so incredibly empty? Why did this specific, immense region of space end up with such a pronounced dearth of galaxies? The most probable answer traces back to the initial conditions of the universe, right after the Big Bang. This region must have originated with a slightly lower density of matter than the average. Over the billions of years that followed, the relentless pull of gravity gradually drew matter out of this region and into the surrounding, slightly denser areas, slowly but inexorably creating the vast void we observe today. However, that leads to an even deeper question: why was this particular region less dense to begin with? That inquiry delves into the very earliest moments of cosmic history. It relates to whatever process was responsible for generating those initial, tiny density variations in the nascent universe. Most cosmologists believe that these crucial variations arose from quantum fluctuations during the inflationary epoch, a brief but incredibly rapid period of exponential expansion that occurred immediately after the Big Bang. These quantum fluctuations were inherently random. By chance, some regions ended up infinitesimally denser, while others became slightly less dense. While most of these variations were incredibly small, occasionally, by pure statistical chance, a larger variation would occur. The Bootes void could very well be the monumental result of one of these rare, larger chance variations in the universe's initial conditions. It's truly remarkable when you pause to consider it. The immense emptiness we observe in the Bootes void today, stretching 330 million light-years across, likely originated as a microscopic quantum fluctuation in the first tiny fraction of a second after the Big Bang. That almost imperceptible, subatomic variation has been amplified and stretched over 13.8 billion years into this colossal supervoid. The universe is strange in such profound ways. The smallest, most fleeting things, given enough time and the right cosmic mechanisms, can have the most enormous and far-reaching consequences. Speaking of the early universe, let's turn our attention to one of the most peculiar and enduring features observed in the cosmic microwave background itself. It's known as the CMB cold spot, and it has been a source of deep perplexity for cosmologists ever since its discovery in 2003. The cosmic microwave background, or CMB, is essentially the ancient afterglow of the Big Bang. When the universe was a mere 380,000 years old, it had cooled down sufficiently for electrons and protons to finally combine and form neutral hydrogen atoms. Prior to this pivotal moment, the universe was an opaque, scorching hot plasma. Photons, the particles of light, couldn't travel very far at all before immediately colliding with free, unattached electrons. After this crucial recombination epoch, the universe became transparent. Photons were then free to travel unimpeded through the cosmos. The CMB is composed of these very photons. They have been journeying through space for an astonishing 13.8 billion years, finally reaching us today as a faint, uniform microwave glow emanating from every direction in the sky. The most astonishing characteristic of the CMB is its incredible uniformity. If you measure its temperature in different directions across the sky, it is almost precisely the same everywhere you look, approximately 2.725 Kelvin, which is just a few degrees above absolute zero. However, there are tiny, subtle variations within this uniformity. Some regions are ever so slightly warmer, while others are a fraction cooler. These temperature differences are incredibly small, about 1 part in 100 Zalausen. These minute variations are critically important. They are the direct imprints of the density fluctuations that existed in the very early universe. Regions that were slightly denser were also slightly cooler in the CMB. These slightly denser, cooler regions eventually grew, through the relentless pull of gravity, to become the galaxies and massive galaxy clusters we observe throughout the universe today. Therefore, the CMB is an incredibly precious and informative relic. It serves as a direct snapshot of the universe when it was just a cosmic infant, only 380,000 years old. By meticulously studying the intricate pattern of these hot and cold spots, scientists can glean invaluable insights into the initial conditions of the universe, providing clues to its very earliest moments. Satellites like CUOB, WMAP, and Planck have mapped the CMB with truly exquisite detail, providing astronomers with an unprecedented view of the universe's infancy. And it was when scientists carefully analyzed these incredibly detailed maps that they stumbled upon something truly unexpected. There is a specific region of the sky, spanning approximately 10 degrees across, that is significantly cooler than what our models predict. This is the infamous CMB cold spot. It's not just a little bit cooler, it's about 70 millionths of a degree Celsius colder than the average temperature of the CMB. While that might sound like an incredibly minuscule difference, in the context of the CMB's otherwise tiny temperature variations, it is remarkably, anomalously large. The cold spot is located in the constellation Eridanus. Its shape is roughly oval, extending about 10 degrees by 5 degrees. To give you a sense of its apparent size, that's roughly 50 times the apparent diameter of a full moon in our night sky. Here's why its existence is so perplexing. Based on our standard cosmological model, we can calculate the probability of such a large and cold region appearing purely by chance. The probability of such a statistical fluctuation is estimated to be approximately 2%. That's not impossible, certainly, but it is quite unlikely. A 2% probability means that if you were to hypothetically run the universe 100 times, each with slightly different random initial conditions, you would expect to observe a cold spot like this in only about 2 of those universes. The fundamental problem is that we live in only one universe. So, either we are simply experiencing a bit of cosmic bad luck and happen to reside in one of those rare 2% universes, or there is something genuinely special and profound about the CMB cold spot that our current models don't account for. Scientists have put forward several potential explanations to try and make sense of this anomaly. One prominent idea suggests that the cold spot is caused by a supervoid. Remember, voids are those vast regions of space with a noticeable absence of galaxies. The hypothesis is that if there's an enormous supervoid located somewhere between us and the cosmic microwave background in that particular direction, photons of light passing through it would lose energy due to a phenomenon known as the integrated Sachs-Wolf effect. Here's a simplified way to understand how this effect works. As photons initially enter a gravitational void, they effectively have to climb out of a slight gravitational potential well, causing them to lose a tiny amount of energy. As they subsequently leave the void, they then fall back into a gravitational well, gaining energy. If the universe were perfectly static and not expanding, these two effects would neatly cancel each other out, and the photons would emerge with the same energy they had when they entered. However, because the universe is continually expanding, the void itself grows larger and becomes less dense while the photons are traversing it. This means that when the photons eventually leave the void, the gravitational well they fall into is shallower than the one they initially climbed out of. As a net result, they gain less energy on their way out than they lost on their way in. The end consequence is that these photons arrive at our telescopes slightly cooler than they otherwise would have been. So, in theory, a supervoid could indeed create a cold spot in the CMB. And, tellingly, astronomers have found some evidence of a large, though not record-breaking, void in the general direction of the cold spot. It's not as enormous as the Boötes void, but it is still a substantial region of emptiness. But here's where the problem arises. Even with the presence of this observed void, the detailed calculations suggest that it can only account for a small fraction of the cold spot's total coldness. You would require an absolutely colossal, truly enormous void, far larger than anything we've observed in that direction, to fully explain the entire effect. And, unfortunately, we simply don't see evidence of a void of that immense scale. Another, far more speculative, theory suggests that the cold spot might be related to a collision between our universe and another universe, a scenario that arises in certain multiverse models. In some versions of cosmic inflation theory, our universe is envisioned as just one single bubble within an infinite, frothing foam of countless other universes. If another such universe, bubble, were to have collided with ours in the very early stages of its existence, it could potentially leave a distinct, circular imprint in the CMB, manifesting as a region that is either colder or warmer than the average. This is, admittedly, an extremely exotic explanation, and there is no direct evidence supporting it beyond the cold spot itself. However, the fact that scientists are even willing to consider such radical ideas highlights just how deeply puzzled they are by this anomaly. It suggests that conventional explanations simply aren't quite working. A third, and perhaps more mundane, possibility is that the cold spot is merely a statistical fluke. A 2% probability, while rare, is certainly not impossible. Perhaps we just happen to inhabit a universe where this unlikely feature, this rare random deviation, simply exists by chance. Sometimes, genuinely rare things do occur. The inherent challenge here is that we only have one CMB to observe. We cannot rerun the experiment. We can't create 100 different universes and then count how many of them happen to exhibit cold spots. We are limited to a single data point, the universe in which we live. This makes it incredibly difficult to definitively ascertain whether the cold spot is a truly meaningful anomaly, hinting at new physics, or just a random chance occurrence. If we had, say, 10 universes to observe, and 9 of them displayed no such cold spot, we could then say with much greater confidence that the cold spot in our own universe is indeed significant. But we don't have that luxury. As of 2025, the CMB cold spot remains an unexplained enigma. It might be partially caused by a supervoid, but likely not entirely. It might be a statistical fluke, but that feels somewhat unsatisfying as an explanation for such a prominent feature. It might even be evidence of exotic, completely unknown physics, but that remains highly speculative. What is undeniably clear is that it is anomalous. It distinctly stands out in the detailed maps of the CMB. It is both larger and colder than our current models predict it should be. And until we arrive at a truly convincing explanation, it will continue to be one of the strange things in our universe that we simply don't fully comprehend. Now, let's turn our attention to a star that appears to defy the very rules of nuclear physics, or at the very least, seems to. It is officially named HD Lun 1065, but astronomers often refer to it as Przybylski's star, a name given in honor of the astronomer who first studied it extensively. This peculiar star is situated approximately 370 light-years away from us, nestled in the constellation Centaurus. From a casual distance, Przybylski's star appears completely normal. It's an A-type star, roughly twice as massive as our Sun and about 6 times more luminous. Nothing overtly unusual there, at least not at first glance. However, when astronomers meticulously analyzed its light spectrum, which is like a unique chemical fingerprint of a star's composition, they discovered something absolutely bizarre. The star contains elements that, according to everything we know about stellar evolution and nuclear processes, simply shouldn't exist in any star for more than a few weeks. Specifically, its spectrum shows clear evidence of technetium, promethium, and other highly radioactive elements that possess extremely short half-lives. Let me explain precisely why this poses such a significant problem. Stars are essentially cosmic furnaces that create elements through the process of nuclear fusion. In their fiery cores, hydrogen atoms are fused together to form helium. In more massive stars, this process continues, with helium fusing into heavier elements like carbon and oxygen. In the most massive stars, the fusion chain extends even further, building up heavier and heavier elements all the way to iron. Elements that are heavier than iron, such as gold or uranium, are generally created in far more energetic events, primarily during supernova explosions. When a massive star reaches the end of its life and violently explodes, the incredible pressures and temperatures generated during this cataclysmic event are sufficient to forge these very heavy elements. They are then scattered into the vastness of space, where they can eventually be incorporated into new generations of stars and planets. So, when we observe heavy elements in a star's atmosphere, our general assumption is that these elements were present in the gas cloud from which the star originally formed. The star was born from a cosmic nursery of gas and dust that had already been enriched by the remnants of previous generations of stars, including the heavy elements they produced and scattered. But here's the critical twist. Some heavy elements are inherently radioactive. This means they are unstable and naturally decay over time, transforming into lighter elements. Uranium, for instance, has a half-life of approximately 4.5 billion years. This means that half of any given sample of uranium will decay into lighter elements over that vast period. Even after billions of years, a significant amount of uranium can still be found. Technetium, on the other hand, is a very different beast. It has no stable isotopes whatsoever. Every single known form of technetium is radioactive. The longest-lived isotope, technetium-98, has a half-life of only about 4.2 million years. That is an incredibly short span of time on cosmic scales. Przybylski's star is believed to be several billion years old. Based on its observed characteristics, it's clearly a mature star, not a young, recently formed one. If it had formed with technetium in its atmosphere, that technetium would have completely decayed away billions of years ago. There should be absolutely none left. Yet, when astronomers meticulously observe the star's spectrum, they find clear and undeniable evidence of technetium. They also detect promethium, another highly radioactive element with a short half-life. and they have consistently observed these elements ever since the star was first studied in detail back in the 1960s. So, where is this technetium and these other short-lived radioactive elements actually coming from? There are a few possibilities, but none of them are entirely satisfactory or without their own significant problems. One idea is that the star itself is somehow creating technetium on its surface through some unknown or poorly understood nuclear process. Perhaps there's a mechanism we haven't yet discovered that can produce these elements in the relatively cool outer layers of a star. However, this seems highly improbable. We possess a very robust understanding of nuclear physics, and there are no known processes that could accomplish this in the star's atmosphere. Another theory suggests that the technetium is being dredged up from the star's deeper interior. Perhaps, deep within the star, nuclear reactions are indeed creating technetium, and powerful convection currents are then carrying it up to the surface where we can observe it. But again, this doesn't quite hold up under scrutiny. The star's interior, while hot, isn't believed to be hot enough to create technetium through the normal nuclear reactions we understand. A third, more speculative idea, which honestly sounds like something ripped straight from a science fiction novel, is that the star contains super-heavy elements. These are elements with atomic numbers far exceeding anything we've ever observed naturally. In the realm of theoretical nuclear physics, there's a concept known as the island of stability. The idea is that if you go far enough up the periodic table, beyond the known, fleetingly stable elements, you might encounter a region where certain super-heavy elements are predicted to be relatively stable, at least for much longer durations. Some of these hypothetical super-heavy elements, if they exist, might decay into technetium or promethium as intermediate products in their decay chain. So, Przybylski's star might potentially contain these super-heavy elements, which are slowly decaying and thereby continuously replenishing the supply of technetium and promethium we observe. This is, however, an extremely speculative notion. We have never observed such super-heavy elements in nature. While we've managed to create a few in powerful particle accelerators, they generally decay almost instantly. The island of stability remains a theoretical prediction, not an established fact based on observation. Still, Przybylski's star is so genuinely strange that astronomers are willing to consider even these highly exotic explanations. There's another peculiar aspect to this star: its overall chemical composition. It exhibits unusually high amounts of certain rare earth elements. Its spectrum reveals strong absorption lines for elements such as holmium, dysprosium, and europium. These elements are found in much greater abundance in Przybylski's star than they are in our own Sun. It's classified as what's known as a chemically peculiar star. There are several different types of chemically peculiar stars, and they are generally thought to arise due to complex atmospheric processes that cause certain elements to become concentrated or depleted in the star's outer layers. For instance, radiation pressure and magnetic fields can cause some elements to either sink deeper or float closer to the surface within the star's atmosphere, leading to these unusual abundances. But even among the diverse group of chemically peculiar stars, Przybylski's star is exceptionally extreme. Its abundance patterns are far more pronounced and unusual than almost any other star of its kind, and the persistent presence of those short-lived radioactive elements truly sets it apart. Some astronomers have even wondered if Przybylski's star might have a hidden companion. Perhaps it exists in a binary system with a very dense object, like a neutron star or a white dwarf, and material from this companion is somehow falling onto Przybylski's star, carrying these radioactive elements with it. However, we currently see no evidence whatsoever of such a companion. The star's motion doesn't show the telltale wobble we would expect from an orbiting, unseen partner. As of 2025, Przybylski's star remains an enduring mystery. For over 60 years, astronomers have been diligently observing it. And for over 60 years, its spectrum has consistently displayed technetium and promethium. These elements should have completely decayed away eons ago, yet there they are, stubbornly present. Either there's a nuclear process at work that we simply don't understand, or the star contains some form of exotic, unknown matter, or there's something fundamentally flawed with our observations or how we interpret them. None of these possibilities is particularly comforting, which is precisely why Przybylski's star holds its place as one of the strangest objects in the vast expanse of the night sky. Let's now recount an extraordinary event that took place on October 19, 2017. On that day, astronomers using the Pan-STARRS telescope in Hawaii detected something unusual moving through our solar system. Initially, they presumed it was just another comet or asteroid, a routine discovery. However, as they gathered more and more data, they quickly realized that this object was profoundly different, unlike anything they had ever encountered. They named it Oumuamua, a Hawaiian word that translates to scout or messenger, a truly fitting name given its origins. Oumuamua came from outside our solar system, from the depths of interstellar space. It approached from the general direction of the constellation Lyra, swiftly passed through the inner regions of our solar system, and then began its journey back out into the interstellar void. We had only a few precious weeks to study it before it became too faint and too distant for our telescopes to observe effectively. What we managed to learn during those fleeting weeks was both utterly fascinating and deeply perplexing. Oumuamua was strange, remarkably strange, in multiple ways. First, consider its shape. Based on how its brightness fluctuated as it tumbled and rotated through space, astronomers calculated that Oumuamua was incredibly elongated. The best estimates suggested it was roughly 400 meters long, but only about 40 meters wide. That gives it an astonishing length-to-width ratio of about 10:1. It was either distinctly cigar-shaped or, potentially, more like a flattened pancake, depending on the precise angle and geometry. This is highly unusual for cosmic bodies. Most asteroids and comets tend to be more spherical, or at least irregularly lumpy, but rarely are they so long and slender. While an elongated shape like Oumuamua's is theoretically possible, it is exceptionally rare among naturally occurring objects we've observed. Second, let's look at its surface. Oumuamua exhibited a reddish hue, similar in color to some of the ancient objects found in the outer reaches of our own solar system. This reddish tint suggested that its surface had been exposed to the harsh environment of cosmic rays for an extended period, which can gradually redden surface materials. So far, that aspect seemed relatively normal. However, Oumuamua showed absolutely no signs of a coma. Comets, as they approach the Sun, heat up significantly. The various ices on their surface vaporize, creating a vast, diffuse cloud of gas and dust around them, known as a coma. It is this coma that gives comets their characteristic fuzzy appearance and often leads to the formation of a tail. But Oumuamua had no coma. Even when it passed incredibly close to the Sun, well within the orbit of Mercury, no discernible coma appeared. This strongly indicated that it was not a comet, at least not a typical icy comet like those we're familiar with. Perhaps it was more akin to an asteroid, composed primarily of rock or metal. But then came the truly bizarre observation. Oumuamua's trajectory, its path through space, didn't quite match what we expected based on gravitational forces alone. After it rounded the Sun and was accelerating away, heading back out of the solar system, it was speeding up slightly more than it should have been. When scientists calculate an object's trajectory, they meticulously account for the gravitational pull exerted by the Sun and all the planets. These gravitational forces are incredibly predictable. Based solely on gravity, we could precisely forecast Oumuamua's exact position at any given moment. Yet, it was moving just a little faster than anticipated. Something other than gravity was subtly propelling it. This kind of non-gravitational acceleration is actually quite common for comets. The evaporating gas molecules streaming away from a comet's coma create a subtle rocket-like effect, providing a tiny but measurable thrust that pushes the comet slightly. This phenomenon is well understood for comets. But, as we've established, Oumuamua didn't have a visible coma. So, what was providing this unexpected push? Scientists proposed several ideas. Perhaps Oumuamua was indeed outgassing, but the gas it was expelling wasn't carrying enough dust to create a visible coma. Maybe it was venting gas from just one side, generating a subtle thrust, but our instruments simply weren't sensitive enough to directly observe it. Some very faint, inconclusive observations did hint at the presence of gas, but it was incredibly difficult to confirm definitively. Another intriguing idea was that Oumuamua was being pushed by sunlight itself. All objects within the solar system experience a tiny amount of radiation pressure from the sun. Photons, particles of light from the sun, strike the object and transfer a minuscule amount of momentum, gently pushing it. For most celestial bodies, this force is incredibly small, utterly dwarfed by the pull of gravity. However, if an object were extremely thin and very light, almost like a cosmic sheet or a sail, then radiation pressure could become a significant force. Perhaps Oumuamua was, in fact, incredibly thin. If it were only a few meters thick, but hundreds of meters across, and composed of relatively light material, then radiation pressure could potentially explain the observed acceleration. But this raises a whole new set of profound questions. How would such an object naturally form? Why would it be so exceptionally thin? It's incredibly difficult to conceive of natural astrophysical processes that would create a thin, rigid sheet of rock or ice hundreds of meters in length. This is where the discussion veered into truly speculative territory. In 2018, two prominent Harvard astronomers, Abraham Loeb and Shmuel Bialy, published a paper that boldly suggested Oumuamua might actually be artificial. More specifically, they proposed it could be a light sail, a thin, reflective sheet specifically designed to be propelled through space by the pressure of starlight. Such a sail could, theoretically, be a spacecraft or a probe dispatched by an advanced alien civilization. This suggestion, as you can imagine, generated an enormous amount of controversy and intense debate within the scientific community. Most scientists remained deeply skeptical. The alien hypothesis is almost always the very last resort in astronomy. You typically only consider invoking intelligent extraterrestrial life when every conceivable natural explanation has been thoroughly exhausted. And, to be fair, there were indeed natural explanations for Oumuamua, even if some of them felt a bit strained or required unusual circumstances. Loeb, however, argued that we should, at the very least, seriously consider the possibility. He pointed out that if Oumuamua were truly artificial, it would undoubtedly represent the most significant discovery in the entire history of humanity. The fact that it might be an unlikely explanation shouldn't, in his view, lead us to dismiss it without rigorous consideration. But the majority of astronomers still lean towards the belief that Oumuamua was a natural object. They think it was likely a comet with highly unusual properties, or an asteroid with a genuinely weird, elongated shape, or perhaps even a fragment of a shattered planet from an entirely different star system. These natural explanations, while still requiring some unique conditions, generally require fewer extraordinary assumptions than the alien hypothesis. The fundamental problem is that we will probably never know for certain. Oumuamua is long gone. It has traveled too far away and become too faint for any of our current telescopes to observe it now. We had only a few weeks to study it, and we simply didn't acquire all the data we desperately wanted. If another interstellar object ever passes through our solar system, we will undoubtedly be much better prepared. We'll have a network of telescopes poised and ready to observe it, allowing us to gather far more detailed and comprehensive data. In fact, a second interstellar object was discovered in 2019. It was named Borisov, and it was definitively a comet. It displayed a clear coma and a distinctive tail, behaving exactly like the comets we observe within our own solar system. Borisov was, in essence, unremarkable, which ironically makes it remarkable. It confirmed that interstellar comets, at least those like Borisov, appear to be very similar to our own solar system's comets. But Oumuamua remains unique. We have never seen another object quite like it, before or since. Perhaps it was simply an exceptionally strange natural object, a cosmic anomaly. Or perhaps it was something more. We will likely never truly know. What is clear, however, is that interstellar objects do occasionally traverse our solar system. The galaxy is teeming with asteroids and comets that have been ejected from their home star systems through gravitational interactions. They drift silently through the vastness of interstellar space, and some of them, purely by chance, pass through our solar system. We now possess the technology to detect them, and every single one we discover, whether mundane or mysterious, teaches us something new and valuable about the universe beyond the comforting confines of our own sun. In June of 2018, telescopes positioned across the globe detected an incredibly bright explosion in a distant galaxy, located some 200 million light-years away. They officially labeled it AT-2218 Cow. The AT part of the name comes from the automated naming system used for astronomical transients, events that appear suddenly and then fade. The cow part is simply a random sequence of letters assigned by the system, but it quickly became the informal nickname for this extraordinary event. At first, astronomers presumed it was a supernova. Supernovae are the violent, spectacular explosions of dying stars, and they occur with regularity across the universe. We detect dozens of them every single year. But as scientists gathered more and more data on AT-2218 Cow, they quickly realized it was profoundly different, unlike any supernova they had ever witnessed. First, its sheer brightness was astonishing. It was approximately 10 to 100 times brighter than a typical supernova, and it reached this peak luminosity with incredible speed. Most supernovae take several weeks to gradually build up to their maximum brightness. AT-2218 Cow, however, rocketed to its peak brightness in just a few days. Then, it faded away just as quickly. Most supernovae remain visible for many months, slowly diminishing in intensity over time. AT-2218 Cow, by contrast, faded significantly within mere weeks. It was as if someone had flicked on a cosmic flashlight, shone it intensely for a very brief moment, and then immediately switched it off again. The light spectrum of this event was also highly unusual. It simply did not match the spectra of any known types of supernovae. The temperatures involved were extraordinarily high, reaching tens of thousands of degrees Celsius, and the explosion itself appeared to be expanding at an astonishing velocity, a significant fraction of the speed of light. Astronomers were utterly baffled. What kind of cosmic explosion could be this bright, this fast, this hot, and so fundamentally different from anything they had previously observed? They soon realized that AT-2218 Cow wasn't an isolated incident. As they meticulously sifted through archival data and continued to monitor the skies with improved instruments, they began to find more events that shared its strange characteristics. These ultra-fast, ultra-bright transients appeared to represent an entirely new class of astronomical phenomena. They are sometimes referred to as fast blue optical transients, or FBOTs. The name describes them perfectly. They are fast, peaking and fading within days or weeks. They are blue, emitting vast amounts of ultraviolet light, which is a strong indicator of extremely high temperatures, and they are optical transients, meaning they appear and then disappear in visible light. As of 2025, we have identified only a handful of these events, perhaps a few dozen in total. They are either genuinely rare, or at least rarely detected, and we still don't fully comprehend what causes them. Several intriguing theories have been proposed. One idea is that they represent the birth of black holes or neutron stars. When a massive star reaches the end of its life, its core collapses under its own immense gravity. If the core is sufficiently heavy, it will form a black hole. If it's slightly lighter, it will form an incredibly dense neutron star. This violent collapse releases an enormous amount of energy. Normally, the majority of this energy goes into blowing apart the outer layers of the star, creating a classic supernova. But in some very specific cases, perhaps the energy is released in a dramatically different way. It might create a powerful, focused jet of material that punches through the star's outer layers and blasts out into space. This highly energetic jet would then create a bright, fast transient that looks distinctly different from a normal supernova. Another theory suggests that FBOTs are the result of a star being violently torn apart by a black hole. This catastrophic process is known as a tidal disruption event. If a star happens to wander too close to a black hole, the black hole's immense gravitational forces will rip the star apart. The stellar material then spirals inward towards the black hole, heating up to extreme temperatures and emitting colossal amounts of energy. Tidal disruption events are known to occur, and they can indeed be incredibly bright. However, most known tidal disruption events unfold more slowly than FBOTs. They typically take months to reach their peak brightness and then gradually fade. FBOTs are much, much faster. Perhaps FBOTs are a special, more extreme type of tidal disruption where a relatively small black hole tears apart a compact object like a white dwarf or a neutron star. The dynamics of such an event would be vastly different, potentially explaining their incredible speed and luminosity. A third idea involves the intense interactions between two compact objects. Perhaps a white dwarf star collides with another white dwarf, or a neutron star, or even a black hole. Such a violent collision would release an unimaginable amount of energy in a very brief, intense burst, creating an FBOT. The truth is, we simply don't know yet. FBOTs are such a new class of phenomena that we are still in the very early stages of understanding their fundamental properties. Every new detection provides us with more precious data, helping us to narrow down the range of possibilities. What makes FBOTs particularly exciting is that they represent something genuinely novel and unexpected. Astronomers have been diligently studying supernovae for centuries. We've developed extremely detailed models of how different types of supernovae work, and we thought we had a pretty good handle on exploding stars. Then, along comes AT2018 Cow, and it completely breaks all the established rules. It's brighter, faster, and fundamentally different from anything we had anticipated. Its appearance forced astronomers to confront the reality that there are types of cosmic explosions they hadn't even imagined were possible. This kind of paradigm shift happens periodically in science. You believe you have a solid understanding of a particular phenomenon, and then nature delivers a complete surprise, a curveball. You detect something that simply doesn't fit into your carefully constructed models. That's precisely when science becomes truly thrilling, because it signifies that there's something entirely new to learn, a fresh frontier of knowledge waiting to be explored. As telescopes continue to improve and we monitor more of the sky with greater frequency and sensitivity, we will undoubtedly detect more FBOTs. Each one will offer crucial clues. Over time, through persistent observation and analysis, we will eventually decipher what is causing them. But for now, in 2025, They remain one of the most strange and unexplained phenomena in the vast and mysterious universe. Let me tell you about a star that, according to our calculations, really shouldn't exist in its current form. Its formal designation is HD 420283, but astronomers affectionately call it the Methuselah star. This name is a direct reference to the biblical figure who was said to have lived for an astonishing 969 years, perfectly capturing the star's seemingly impossible age. The Methuselah star is located approximately 190 light-years away from Earth. If you know precisely where to look, it's actually visible with a good pair of binoculars in the constellation Libra. It's an ancient star, classified as a subgiant. This means it has already exhausted the primary hydrogen fuel in its core and is beginning to evolve off the main sequence, moving towards the later stages of its life. Stars like this are incredibly old. They formed in the very early universe, a time when conditions were vastly different from what we observe today. By meticulously studying these ancient stellar relics, we can gain invaluable insights into the history and evolution of the entire universe. Astronomers employ several sophisticated methods to estimate a star's age. One primary technique involves examining the star's chemical composition. The universe, in its infancy, began with an almost pure mixture of hydrogen and helium. Over cosmic time, successive generations of stars have diligently created heavier elements through the process of nuclear fusion in their cores, and then scattered these elements into space through violent supernova explosions. These heavier elements, which astronomers collectively refer to as metals, see anything heavier than hydrogen and helium, gradually accumulate and enrich the interstellar medium over billions of years. Therefore, a star with a very low abundance of metals likely formed very early in the universe's history, before many generations of stars had enriched the cosmic gas clouds with these heavier elements. The Methuselah star exhibits extremely low metallicity. It contains approximately 250 times less iron than our own Sun. This chemical signature strongly suggests that it formed very early, when the universe was young and heavier elements were still exceptionally rare. Another crucial method for estimating a star's age involves observing its rate of nuclear fuel consumption. Stars primarily fuse hydrogen into helium in their cores. Once this core hydrogen is depleted, they begin to fuse helium into even heavier elements. The rate at which these nuclear reactions occur depends critically on the star's mass and its exact chemical composition. By carefully observing a star's fundamental properties, such as its temperature, its luminosity, how much light it emits, and its precise chemical makeup, astronomers can estimate how long it has been burning its nuclear fuel and, consequently, how old it is. When astronomers applied these well-established methods to the Methuselah star, they arrived at a deeply uncomfortable result. The star's estimated age consistently came out to be around 14 billion years, with a margin of error that, troublingly, overlapped with the age of the universe itself. Herein lies the fundamental problem. The universe itself is only about 13.8 billion years old. We know this with a high degree of confidence from multiple, independent measurements. Observations of the cosmic microwave background, precise measurements of the universe's expansion rate, and the calculated ages of the oldest star clusters all consistently point to an age of approximately 13.8 billion years. So, how can a star possibly be around 14 billion years old in a universe that is only 13.8 billion years old? The error bars, those statistical uncertainties in the measurement, technically allow for an age that is just barely younger than the universe, but it cuts it incredibly close. That's an uncomfortably tight fit, leaving virtually no time for the star to have formed and begun its life. Initially, when this perplexing result first emerged, some individuals suggested that perhaps our measurement of the universe's age was incorrect. Maybe the cosmos was older than we thought. However, as measurement techniques have steadily improved and become more precise, the universe's age has become much more firmly established. It is definitively around 13.8 billion years, with increasingly small error bars. Therefore, the problem must lie with the star's age estimate. But how could we be wrong about the star's age? The methods used for estimating stellar ages are robust and well-established, founded on solid principles of nuclear physics and stellar evolution. The key lies in those error bars. The Methuselah star's age is indeed around 14 billion years, but with uncertainties that technically allow for it to be as young as, say, 13.7 or 13.8 billion years. That's just barely younger than the universe's confirmed age. An incredibly close call, but it is technically within the realm of possibility. If the star formed very, very soon after the Big Bang, perhaps within the first few 100 million years, then it could potentially be that old. However, even this scenario remains uncomfortable. The very first stars in the universe, known as population Athuri stars, were fundamentally different from stars today. They formed from pristine gas composed almost entirely of pure hydrogen and helium, with absolutely no heavier elements. These first-generation stars were likely very massive and, consequently, very short-lived. The Methuselah star, with its observed metallicity, doesn't quite fit the profile of a true first-generation star. Second-generation stars, which formed from gas that had been enriched by the first supernovae, would contain some small amounts of heavy elements. The Methuselah star's low but non-zero metallicity is consistent with it being a second-generation star. But second-generation stars wouldn't have formed immediately after the Big Bang. It would have taken a significant amount of time for the first stars to live their short, intense lives, die in spectacular supernovae, and then enrich the interstellar medium with their newly forged heavy elements. This process would likely have taken at least a few 100 million years. So, the Methuselah star probably formed at least a few 100 million years after the Big Bang. That would, in turn, make its maximum possible age closer to 13.5 billion years or even less. The persistent problem is that observations and calculations continue to suggest it's older than that. Even with improved measurements and refined stellar models, the star's age estimate stubbornly hovers around 14 billion years. And, ironically, the error bars have actually gotten smaller over time, which is the opposite of what we would hope for. We'd prefer the error bars to comfortably encompass a younger age that aligns with the universe's age. So, what exactly is going on? There are a few possible explanations. One is that our models of stellar evolution, particularly for these very old, low metallicity stars, are subtly incorrect in some way. Perhaps these stars evolve differently than we currently think. Maybe there's a specific process we don't yet fully understand that affects their nuclear burning rates over such vast timescales. Another possibility is that our distance measurement to the star is slightly off. Stellar age estimates are highly dependent on knowing a star's precise luminosity, and luminosity estimates, in turn, rely on knowing the star's exact distance from us. If the star is actually closer or farther away than we currently believe, its age estimate would naturally change. Astronomers have measured the distance to the Methuselah star using a technique called parallax. As Earth orbits the Sun, nearby stars appear to shift their position very slightly against the background of much more distant stars. By precisely measuring this tiny shift, astronomers can calculate the star's distance. The Gaia satellite, a revolutionary mission, has measured parallaxes for billions of stars with unprecedented precision, including the Methuselah star. But even with Gaia's incredible accuracy, there's always some residual uncertainty. Perhaps the distance is just slightly different from what we think, enough to bring the age estimate down to something more comfortable and consistent with the universe's age. A third possibility is simply that the star is, in reality, younger than our best estimates suggest, and we are simply on the unlucky end of a statistical distribution. When you measure something with inherent uncertainty, sometimes the true value does fall at the very edge of the error bars, or even slightly beyond what the average suggests. Perhaps the Methuselah star is genuinely 13.5 billion years old, and the 14.5 billion year estimate is simply a statistical fluctuation, a rare outlier in our calculations. As of 2025, the Methuselah star remains uncomfortably old. Astronomers continue to refine their measurements, constantly hoping to resolve this persistent tension between the star's apparent age and the age of the universe. But for now, it stands as one of the truly strange things in the universe, a star that, according to our most precise measurements, seems to be older than the universe itself. Of course, it cannot actually be older. Something about our measurements or our models must be slightly askew. But figuring out precisely what that something is proving to be a complex and time-consuming challenge. And until we do, the Methuselah star will continue to perplex and fascinate astronomers, a silent, ancient question mark in the night sky. Now, here's something truly interesting to ponder. All of these strange discoveries we've discussed tonight might seem entirely unrelated. We've talked about a mysterious radio signal from the 1970s that appeared only once. We've explored a star that dims in ways no other star does. We've delved into gigantic, perfect radio circles surrounding galaxies that we can't explain. We've pondered structures in the universe that are simply too large to exist, according to our current theories. We've examined a vast void of space that is almost completely empty when it should be teeming with galaxies. We've discussed a cold spot in the ancient cosmic microwave background that's far too cold to be a mere coincidence. We've grappled with a star containing radioactive elements that should have decayed billions of years ago. We've considered an interstellar visitor with utterly weird properties. We've looked at cosmic explosions that are brighter and faster than any known type of supernova. And finally, we've pondered a star that appears to be impossibly old. On the surface, they all seem like completely separate, distinct cosmic mysteries. But perhaps, just perhaps, they are not. Maybe, in some profound and as yet undiscovered way, they are all communicating the same fundamental message. That message being, the universe is far more complex, far more intricate, and far more surprising than our current models and theories suggest. That there are fundamental processes, entirely new phenomena, or even entirely different aspects of physics that we simply don't fully understand yet. Consider each anomaly in turn. The WO signal hints that there are types of radio sources out there that we haven't yet identified or categorized. Tabby's star demonstrates that even seemingly ordinary stars can behave in utterly unexpected and perplexing ways. Odd radio circles reveal that galaxies can somehow create, or be associated with, vast structures that we are only just now beginning to perceive. The giant arc and the big ring challenge the very notion that the universe is as uniform as we previously thought on its largest scales. The Botez void suggests that emptiness can be far more extreme and pronounced than our current models predict it should be. The CMB cold spot tells us that the universe's earliest light holds secrets that defy simple explanation. Przybylski's star points to nuclear processes or exotic matter that stretch our current understanding of stellar composition. Oumuamua, the interstellar visitor, opened our eyes to the reality of objects traveling between star systems, and its strange properties leave us wondering about their origins. The fast blue optical transients show us that even stellar deaths can be far more diverse and energetic than we once believed. And the Methuselah star keeps us humble, reminding us that even our best age, dating techniques might have subtle flaws. Each of these mysteries, taken in isolation, might be dismissed as just an oddity, a singular strange thing that needs a specific explanation. But when considered together, collectively, they begin to paint a powerful and consistent picture. It's a picture of a universe that is still actively surprising us, a cosmos that continues to reveal phenomena we simply didn't expect to find. This pattern, this accumulation of anomalies, is actually quite normal and historically significant in the progression of science. When humanity stands on the very edge of understanding something fundamentally new, you invariably start to encounter anomalies. These are the things that don't quite fit into the existing framework, the observations that stubbornly refuse to be explained by current theories. At first, they often seem like isolated, disconnected problems, minor discrepancies that can perhaps be explained away or ignored. But eventually, someone, a keen observer or a brilliant theoretician, manages to connect the dots. Someone realizes that these seemingly disparate anomalies are all symptoms of something much larger, a deeper underlying principle or phenomenon that we haven't yet grasped. This is precisely how we arrived at the theory of relativity. In the late 1800s, physics was grappling with several persistent problems. For instance, the orbit of the planet Mercury didn't quite match the predictions of Newtonian mechanics. And, more profoundly, the speed of light appeared to be constant for all observers, regardless of their own motion, which was deeply counterintuitive. These seemed like completely separate, unrelated issues. Then, Albert Einstein emerged and demonstrated that both of these perplexing observations could be elegantly explained by the same revolutionary new theory, relativity. It connected the dots, revealing a deeper, more profound truth about space and time. Perhaps that's precisely what's unfolding now with these contemporary cosmic mysteries. Maybe they are all individual pieces of a much larger, grander puzzle. And someday, a future genius will come along and figure out how all these seemingly disconnected observations fit together. They might develop an entirely new theory of physics, or uncover a previously unknown cosmic phenomenon that explains all of them at once, providing a unifying framework for these current anomalies. Or, perhaps not. It's equally possible that each mystery has its own entirely separate, unique explanation. Maybe the WO signal was, in fact, just an unusual comet. Perhaps Tabby's star is indeed enveloped by a particularly complex and extensive dust cloud. Maybe odd radio circles are simply the shock waves from some novel type of galactic event. Perhaps the giant arc is, after all, just a remarkable statistical coincidence, a random alignment of galaxies that appears more structured than it truly is. Maybe Przybylski's star utilizes some unknown nuclear process we haven't yet discovered. We won't truly know until we meticulously investigate and definitively solve each one. But the very possibility that they are connected, that they are collectively communicating something fundamental about the underlying nature of the universe. That's what makes this such an incredibly exciting and fertile period to be studying astronomy. It keeps the wonder alive. Let me share something with you that might initially sound surprising. Some of the most significant and transformative advances in the history of astronomy didn't come from confirming what we already believed, but rather from being completely wrong. They emerged from making observations that directly contradicted what we thought we knew, forcing us to rethink everything. In the early 1900s, astronomers observed distant galaxies and noticed a perplexing pattern. They all appeared to be moving away from us. Even more curiously, the farther away a galaxy was, the faster it seemed to be receding. This observation didn't make intuitive sense. Why would everything in the universe be moving specifically away from us? Did that imply we were somehow at the very center of the cosmos? But as scientists contemplated this phenomenon more deeply, they had a profound realization. This exact pattern would naturally occur If the universe itself was expanding, if the very fabric of space was stretching and growing, then all galaxies would appear to move apart from each other, and those that were more distant would naturally appear to recede faster from our perspective. This groundbreaking observation directly led to the formulation of the Big Bang Theory, the idea that the entire universe originated from a single, incredibly hot, dense point and has been continuously expanding ever since. Nobody had truly expected that. It dramatically contradicted the prevailing view of the time, which held that the universe was static and unchanging. But the undeniable power of the observations compelled astronomers to completely change their minds, and that unexpected, contradictory observation became the bedrock upon which modern cosmology is built. In the 1960s, astronomers made another astonishing discovery: quasars. These initially appeared as mere points of light, much like ordinary stars, but they possessed truly bizarre properties. They were unbelievably bright, radiating more energy than entire galaxies combined. And yet, they were located incredibly far away, billions of light years distant. Nothing we understood about how stars worked could possibly explain how they could generate such immense luminosity. Eventually, scientists came to the groundbreaking realization that quasars were not stars at all. They were, in fact, the incredibly active, super-energetic centers of distant galaxies, each powered by a supermassive black hole that was ravenously consuming matter. As gas and dust spiraled into these colossal black holes, they heated up to unimaginable temperatures, emitting enormous amounts of energy, and creating the brightest, most sustained sources of light known in the universe. This discovery fundamentally altered how we perceived galaxies. We realized that most large galaxies harbor supermassive black holes at their very hearts, and these black holes play a crucial, dynamic role in the evolution of galaxies themselves. None of this was known before quasars forced us to completely reconsider what was astronomically possible. Then, in the 1980s, astronomers conducting precise measurements of the universe's expansion fully expected to find that it was gradually slowing down. The collective gravitational pull from all the matter and energy in the universe should, logically, be working to pull everything back together, thereby decelerating the expansion. But when they performed meticulous measurements using distant supernovae as cosmic mile markers, they discovered the exact opposite. The expansion of the universe was actually accelerating. This made absolutely no sense based on existing physics. What force could possibly be pushing the universe apart? This utterly confounding observation led directly to the conceptualization of dark energy, a mysterious and pervasive force that is now believed to constitute about 68% of the universe's total energy content. We still don't fully understand what dark energy is, but we know, with high confidence, that it exists because the observations unequivocally demand it. Each of these monumental discoveries began with an observation that simply did not make sense, something that directly contradicted established expectations. And each time, instead of dismissing the observation or assuming it was erroneous, astronomers bravely followed where the evidence led. They modified their cherished theories to align with the new reality revealed by observation. That, fundamentally, is how science operates. And that is precisely what is happening right now with the various cosmic mysteries I've described tonight. We possess a growing body of observations that stubbornly refuse to fit into our current scientific understanding. We could easily ignore them. We could choose to believe they are merely measurement errors or statistical flukes. But that is not the spirit of scientific inquiry. Instead, we take these anomalies very seriously. We study them with meticulous care. We strive relentlessly to comprehend them. And perhaps, just perhaps, they will lead us to the next monumental breakthrough in our understanding of the universe. The reason we are unearthing so many strange and perplexing things in space right now isn't because the universe has suddenly become stranger or more unpredictable. It's because our scientific tools have become dramatically better. We now possess the capability to see things we simply couldn't perceive before. We can measure phenomena with a precision that was unimaginable in previous eras. Think back to the WOO signal. It was detected by a radio telescope in 1977. That telescope, the Big Ear, was by today's standards a relatively simple instrument. It was certainly capable of detecting strong radio signals, but it couldn't pinpoint their exact location with great accuracy. It also lacked the sophisticated capabilities to analyze the signals in truly fine detail. Today, we have infinitely better radio telescopes. Consider the Very Large Array in New Mexico, the ALMI Array high in the Atacama Desert of Chile, and the upcoming Square Kilometer Array, which is being constructed to be the most sensitive radio telescope ever built. These advanced instruments can detect signals that are vastly fainter. They can pinpoint the precise location of sources with incredible accuracy, and they can analyze radio signals in truly astonishing detail, extracting far more information. If the WOO signal were to occur today, we would undoubtedly learn so much more about it. We would know its exact origin point. We would understand its properties with much greater precision. We might even be able to definitively determine what caused it. The same principle applies to all these cosmic mysteries. We are discovering them because we have superior tools at our disposal. And as our tools continue their relentless march of improvement, we will inevitably find even more. Crucially, we will also gain a much deeper understanding of the strange phenomena we've already identified. Tabby's star, for example, was initially discovered by the Kepler Space Telescope, which launched back in 2009. Kepler's primary mission was specifically designed to find exoplanets by meticulously watching for the tiny, characteristic dips in a star's light that occur when a planet passes in front of its host star. It continuously monitored over 150,000 stars for several years. Before Kepler, this kind of continuous, broad-scale monitoring simply wasn't possible. We had to observe each star individually in limited time slots, and we couldn't maintain an unbroken watch on so many. Tabby's star's incredibly weird, irregular dimming pattern would have been almost impossible to detect with earlier technology. But Kepler's unprecedented ability to continuously monitor thousands of stars simultaneously revealed something nobody expected. We weren't even looking for it, we were searching for planets. But Kepler's persistent gaze uncovered a stellar behavior that defied all expectations. Now, we have even more advanced instruments. There's TS, the Transiting Exoplanet Survey Satellite, which is carrying on similar vital work, surveying nearly the entire sky for transiting exoplanets. We have the James Webb Space Telescope, which can observe in infrared light with truly incredible sensitivity, peering back into the universe's infancy and examining the atmospheres of distant worlds. On the ground, we have increasingly powerful telescopes equipped with adaptive optics, which can correct for the blurring effects of Earth's atmosphere, allowing them to see almost as clearly as space telescopes. Each of these instruments, with its unique capabilities, has the potential to uncover entirely unexpected things. Each one provides us with a fresh perspective, a new way of looking at the universe. And the more ways we look, the more strange and wondrous things we find. In the coming years, we will have access to even more extraordinary tools. The extremely large telescope, for instance, is currently under construction in Chile. When it's finally completed, it will boast a primary mirror an astonishing 39 meters across. That is an absolutely enormous light collecting surface. It will possess the unparalleled ability to observe incredibly faint and distant objects with unprecedented clarity. It will even be able to analyze the atmospheres of exoplanets in exquisite detail, searching for the subtle biosignatures that could indicate the presence of life. The Square Kilometer Array, another monumental project, when fully operational, will have a total collecting area equivalent to 1 square kilometer. That's approximately 250 acres of interconnected radio receivers spread across 2 continents. It will be an astounding 50 times more sensitive than any current radio telescope on Earth. If there are any other powerful radio signals out there, like the mysterious WOW signal, the Square Kilometer Array will almost certainly find them. NASA is also actively planning new generations of space telescopes. Some of these will be specifically designed to search for signs of life on exoplanets with even greater precision. Others will focus on unraveling the mysteries of the early universe, peering back in time to the very first galaxies. Still others will be tasked with mapping out the elusive dark matter that pervades the cosmos. Each of these future instruments will carry the immense potential to discover something completely unexpected, to reveal entirely new aspects of reality. And here's the consistent, undeniable pattern: every single time we construct a more powerful, more sensitive telescope, we uncover surprises. Every single time. There has never been a single instance where we built a more advanced instrument and found only exactly what we expected, with nothing more, nothing new. The universe, without fail, always manages to surprise us. So, we can be exceptionally confident that in the coming decades, we will discover even more strange things, encounter more perplexing mysteries to ponder, and make more observations that simply don't quite fit our existing theories. And that, fundamentally, is what makes science so exciting. Mysteries are not roadblocks, they are the engines of progress. They compel us to think harder, to rigorously question our ingrained assumptions, and to develop entirely new ideas and conceptual frameworks. They push the boundaries of what is known. Let me tell you something important about the people who dedicate their lives to studying these cosmic mysteries. They are not some distant, detached group of super, intelligent beings who have already figured everything out. They are regular people, just like you and me. They are individuals who get genuinely thrilled, almost childlike in their excitement, when they encounter something truly weird and inexplicable in their data. They are people who stay up late into the night, fueled by curiosity, tirelessly trying to make sense of confusing observations. They are passionate individuals who engage in lively, sometimes heated, debates with their colleagues about what certain observations truly mean. When Jerry Emin, back in 1977, saw the WOW signal, he was poring over physical paper printouts of data. The Big Air telescope recorded its findings as a series of numbers on these printouts, indicating signal strength at different frequencies. Most of the time, those numbers were low, merely reflecting the background noise of the cosmos. But on that particular printout, there was a sequence of numbers that was dramatically different, soaring far above the typical background levels. Emin, in a moment of sheer astonishment and exhilaration, grabbed a red pen and circled that sequence. Next to it, in bold, handwritten letters, he scrawled WOW. He was genuinely surprised and deeply excited by what he saw. That spontaneous, human reaction is precisely how the signal acquired its iconic name. It wasn't some formal, pre-planned designation. It was one person's immediate, visceral response to witnessing something utterly unexpected and potentially profound. That raw sense of wonder and surprise is still a vibrant, essential part of astronomy surface. It will possess the unparalleled ability to observe incredibly faint and distant objects, pushing the boundaries of what we can perceive. It will also be capable of analyzing the atmospheres of exoplanets in unprecedented detail, searching for potential signs of life far beyond our solar system. The Square Kilometer Array, when fully completed, will have a total collecting area equivalent to 1 square kilometer. That's roughly 250 acres of radio receivers, all working in unison. It will be an astounding 50 times more sensitive than any current radio telescope. If there are other radio signals out there, akin to the WOO signal, the square kilometer array will undoubtedly find them. NASA is also meticulously planning new generations of space telescopes. Some of these will be specifically designed to search for definitive signs of life on exoplanets. Others will focus on studying the very early universe, peering back to cosmic dawn. Still others will aim to map out the mysterious distribution of dark matter throughout the cosmos. Each of these ambitious instruments, with its specialized capabilities, holds the profound potential to discover something completely unexpected and revolutionary. And here's the consistent, undeniable pattern that history has shown us every single time we construct a better, more sensitive telescope, we uncover surprises. Every single time, without exception, there has never been a situation where we built a more advanced instrument and found precisely what we expected, and nothing more. The universe consistently, reliably, and beautifully surprises us. So, we can be extremely confident that in the coming decades, we will discover even more strange things, more profound mysteries to meticulously puzzle over, and more observations that simply refuse to fit neatly into our existing theories. And that, fundamentally, is an incredibly exciting prospect, because mysteries are not obstacles, they are the most powerful drivers of scientific progress. They compel us to think harder, to rigorously question our most cherished assumptions, and to develop entirely new ideas and frameworks. Let me share a little bit about the people who dedicate their lives to studying these mysteries. They aren't some distant, aloof group of super, intelligent beings who have everything perfectly figured out. They are, in essence, regular people. They are individuals who get genuinely excited, almost childlike in their wonder, when they stumble upon something truly weird and unexplained. They are people who willingly stay up late into the night, tirelessly trying to make sense of confusing and contradictory data. They are people who engage in passionate, sometimes heated, arguments with each other about what specific observations truly mean. When Jerry Emmon first saw the WOO signal back in 1977, he was literally reviewing paper printouts of data. The Big Ear telescope, in those days, recorded its findings as long columns of numbers on physical paper, with each number indicating the strength of a detected signal. Most of the time, these numbers were low, simply representing the ubiquitous background noise of space. But on that particular printout, there was a sequence of numbers that was distinctly different, dramatically higher than the background. Emmon, in a moment of sheer astonishment, grabbed a red pen and circled that sequence. Right next to it, he scrawled the single word, WOWO. He was genuinely surprised, deeply excited, and utterly bewildered. That's precisely how the signal received its enduring name. It wasn't some formal, official designation decided by a committee. It was one person's spontaneous, human reaction to encountering something utterly unexpected and extraordinary. That raw human reaction, that profound sense of wonder and surprise, remains a vital and integral part of astronomy today. When Tabby's star was initially discovered, the astronomers who were studying it were genuinely puzzled. They understood that they were observing something truly unusual, something that defied easy explanation. They worked incredibly hard, exploring every conceivable angle to try and explain it. When conventional, established explanations repeatedly failed, they were forced to consider unconventional ones, including, however reluctantly, the possibility of an alien megastructure. That suggestion, as you might imagine, was highly controversial. Many scientists criticized it, believing it was irresponsible to even mention aliens when other, more natural, explanations might eventually emerge. But the scientists who proposed it weren't asserting that it definitely was aliens. They were simply stating, with scientific honesty, that they couldn't definitively rule it out. And that, in itself, is a testament to the scientific process. When you encounter an observation that you simply cannot explain with existing knowledge, you are ethically bound to consider all possibilities, even the ones that seem highly unlikely. This is what science truly looks like from the inside. It is not a smooth, linear process where everyone always agrees and everything immediately makes perfect sense. It is often messy. People disagree vehemently. They engage in intense debates. They argue passionately about interpretations of data. They propose ideas that, more often than not, turn out to be wrong. But through all this necessary messiness, progress inexorably happens. Someone makes a critical observation. Other researchers then strive to independently confirm it. People propose various explanations. They then rigorously test those explanations through further observation and experimentation. Some explanations are definitively ruled out. New observations are made, bringing fresh data to the table. And gradually, painstakingly, a clearer understanding begins to emerge. The scientists who have been studying Przybylski's star have been perplexed for many decades. They've put forward numerous explanations for the presence of those short-lived radioactive elements in its atmosphere. None of those explanations have entirely resolved the paradox. But they persist. They continue to make observations. They continue to refine their ideas. That unwavering persistence, that refusal to give up when things are confusing or difficult, is what truly propels science forward. It's about trusting that eventually, with enough dedicated effort and thoughtful inquiry, understanding will emerge.